Welcome everyone. In this video, we're going to look at the SCION data plane in more detail. I hope you had a chance to first look at the SCION architecture overview video to gain some intuition of how the system works, as well as the control plane video to understand how path exploration and dissemination works. In this video, we will then look more at the technical details of how a sender combines path segments and sends packet through the network. We're going to talk about the SCION data plane overview, and in particular, we're going to look at path lookup, path combination, and path encoding in the packet. More details are available in the SCION book in chapters 2.2 and 8. Let's start with path lookup. So here are the steps that a host performs to obtain path segments to communicate with a given destination. Similar to today's internet, oftentimes a host starts with a name that the user can understand. The user may type www.scion-architecture.net into a browser, and then this name needs to be translated into an address and a path through the network. In SCION, the way this works is that the RAIN system, which is the name resolution architecture, is being contacted with this name www.scion-architecture.net, for instance, and the RAIN's infrastructure will respond to the host with an isolation domain, an autonomous system inside this isolation domain, and a local address. In today's internet, the DNS system performs the same operations, and in essence just returns local IP addresses or a set of IP addresses to the host. In SCION, the IP address or the local address is actually not very important to send the packet to the destination. What's most important is the isolation domain and the autonomous system. The local address is essentially only looked at the destination AS. So once a host receives the isolation domain X, the autonomous system Y, and the address C, the host will then contact the local path server to obtain path segments. And this looks as follows. The host sends to the path server a request of the ISD X and ASY. And the path server responds with up paths, path from the local AS to the core, with a core path, as well as down path segments from the remote core AS to the remote ASY. Now the host can combine these path segments to obtain end-to-end paths, and these paths are then added to the packets themselves to be sent through the network. So let's look at the path lookup in a bit more detail. And we've already seen this also in the previous video on the control plane. The next two slides are a repetition from that video. So in the local ISD, the client can request path segments from its local path server. And here we're going to look at an example of a host inside ASR that intends to communicate with a host in ASS. So the host sends a path request to its local path server using the same of also the blue ISD in this example and the destination ASS. And if the down segments of ASS are not locally stored, the local path server then sends the requests to the core path server and fetches the required down segments. Finally, the local path server replies to the host with up segments to the local ISD core, and we can see an example here of these yellow and orange paths going to core ASK and core ASL. And these would be a sample of up paths provided to the host, and then also a sample of down paths that were fetched. And in this example, again, the yellow path goes to core ASK, the orange to core ASL, and the red path to core ASM. Now, some of the up path segments and down path segments are not directly connected. They don't lead to the same core ASs. So in addition, core paths that link the core ASs that are shown in blue here are being provided to the end host. And now the end host has a number of different paths to combine to create an actual end-to-end path from ASR to ASS. We've also taken a look at how this path lookup looks like for looking up a AS in a remote ISD. And again, the local path server may have all the information already stored. However, in the case the local path server does not store the core segments and the down segments from the destination AS, they have to be fetched from a core path server. So in the example in this slide, we're going to look at a host in ASS that intends to communicate with a host in ASE prime within the green ISD. And if the local path server does not have the paths cached, a core path server, in this example in ASM, is being contacted. And in case this core path server does not have the required information, a core path server in the remote ISD is being contacted. So finally, up paths are being also returned to the host, as well as core paths linking the up path ASs with the down path ASs, and also a set of down path ASs are being provided. And as you can again see here, several path combination will work to create an end-to-end path from S to E prime. To perform the actual path combination, SCION offers a lot of different ways to combine paths. Here we see the 8 different ways in which path segments can be combined. The orange arrows depict up and down path segments, and the orange segments that are dashed, that are horizontal as well, depict core path segments. So essentially, PCBs find these orange segments. Now the blue lines represent actual data path or regular path segments that were combined. So if a peering link is being traversed, we depict this with a dashed blue line, and also the circles have representation. So the gray circles represent core ASs, the white circles non-core ASs, and the source and destination are represented by a smaller blue circle. So we see there are 5 different case 1 types, and in this case, the end-to-end packet will traverse a core AS. So no shortcut is being used, while the path segments are directly being used. Cases 2, 3, and 4 represent shortcuts. First, case 2 represents a peering link shortcut, case 3 an AS level shortcut, and case 4 a non-path shortcut where the destination is directly in an AS on the up path segment. Now we're going to look at some examples here. If you'd like to see all the different examples worked out, you can also take a look at our book, which has more detailed descriptions about each case. The first example we're going to look at is a core segment combination. So in this example, we have a source in ASR that intends to communicate with a destination ASS, and the following 3 path segments are being used to create the end-to-end path. So an up path segment leading from ASR through ASQ, ASN, and K to a core segment leading from ASK to ASM, and combine that with a downpath segment leading through ASs M, P, and S, can be combined to form this blue end-to-end path. In a second example, we're looking at a shortcut where, and in this case specifically into a peering shortcut, where an up path segment and a down path segment offer the same peering link. So in this example here, the source host in R intends to communicate with the destination ASS, and we see there's a shortcut link between ASs O and P. And now the sending host can make use of this shortcut by sending a packet directly across the path ROPS. Shortcuts also work across isolation domains. So in this example, we have a source host in ASS communicating with a destination host in ASX, and there's an inter-ISD shortcut link leading from P to X. And here we see the 3 paths, an up path SPM with a core path and the destination path, down path YX. However, again, this shortcut can be used to directly communicate from P to X. SCION essentially is a transparency architecture that offers the source host explicit information about where the packet traverses. So this ISD transition can still be seen from the pop fields in the packet header. So both the source and the destinations are aware which ISDs were traversed from the source to the destination. The final example we're going to look at is an AS shortcut example. So here, a source host in R intends to communicate with the destination in ASS, and we can see that the two paths that are being shown intersect at ASO. Now, when an end-to-end path is being formed, the packet does not have to go through the ISD core, but it can directly go from R to O to S, as we can see in this example. So the actual packet will follow the blue path, which represents this shortcut through the two orange paths. Next, we're going to look at the path construction of the actual hop fields in the end-to-end path. And in this example, we look at a combination of an up segment, a core segment, and a down segment. And each path segment contains an information field, as we've seen in the video, on the control plane. The information field contains information such as the timestamp, as well as the isolation domain number. We can see that the up segment contains also three hop fields for ASs A, B, and C, which also include interface identifiers to exactly identify how the packet should traverse autonomous systems. Now, these information fields and these hop fields are being combined to form the actual forwarding path, which will be placed in the SCION header. Next, we're going to look at more details about these fields and the header itself as well. So first, let's take a look at the SCION packet header. The SCION common header is only 8 bytes long, and it contains information such as the SCION version number, which is currently 0, the destination and source address types, which are 6 bits each, and the total packet length. We also have a field to encode the header length, and two pointer fields that point to the current information field and the current hop field within the SCION header. We also have the next header, which encodes the type of the next header, if it's a TCP header or an extension header for SCION. Now, the source and destination addresses in SCION can have different types. And we have the structure at the bottom, you can see, which encodes the source and destination addresses. So in order to have fixed locations for the destination ISD and destination AS, we have first the destination ISD, destination AS, followed by the source ISD and source AS. As the local addresses can be variable sized, we list them afterwards. So the destination host address goes first, and so that the destination address is always at a fixed location in the packet, but then the source address is at a variable size location, as the destination host address can be of different types. So for instance, here we see an example where the destination address is an IPv6 address and the source address is an IPv4 address. Finally, we pad the information up to a multiple of 8 bytes. Let's talk a little bit more about the information and hop field contents themselves. So the info field provides information about the entire path segment, which can contain of one or multiple hop fields. And the information field itself contains flags that denote if this path segment is used as a peering shortcut, a regular shortcut, or if it's used as an up segment or a down segment. There's also a timestamp contained with the creation time of the PCB and an ISD identifier that identifies the isolation domain. Finally, also the segment length is added, containing how many hop fields are included. Then each hop field again contains some flags, the continue and stop bit, which enables the construction of a hop field that is composed of multiple 8-byte hop fields itself, in case an AS wants to add more than just 8 bytes of information. Additional flags are forward-only, verify-only, or crossover flags. Forward-only enables an AS to denote a hop field that cannot be used for local delivery to clients or hosts within the local AS, only for forwarding. Verify-only and crossover fields that are then being used for the actual MAC field verification and also identification of peering links. The expiration time is a time that is relative to the timestamp in the info field that enables encoding the lifetime of a specific hop field. Then ingress and egress interface identifiers identify the incoming and outgoing links out of an autonomous system. And finally, we have a message authentication code, which enables a cryptographic verification of the hop field contents. We're going to talk about the message authentication code more on a later slide. Let's talk a little bit more about the ingress and egress identifiers. We talked a little bit about these in the previous talk on the control plane, but let's look at this in a little bit more detail. So as we've seen, each AS assigns a unique integer identifier to each interface that connects to a neighboring autonomous system. The interface identifiers essentially identify the ingress and egress links for traversing an AS. And so the ASs then use a local routing protocol to route from the ingress SAN border router to the egress SAN border router. So for example, here we have two different paths, the yellow and the orange path. So for core ASL, the yellow path has the egress interface number 4 traversing through the ingress interface number 3 in ASO and through the egress interface 6 again in ASO. And finally, the path traverses the ingress interface number 1 in ASR. The orange path crosses a different link between L and O, and so we see the ingress-egress interfaces are slightly different, exiting from interface 5 out of ASL and entering into interface 2 in ASO. So with this, we can see that SCION enables selection of different paths across different links that connect different ASs. Within the packet, the information is encoded as follows. So the info field precedes the hop fields. And on this diagram, we see the example where we combine an up path with a core path and a down path. And here the arrows on the paths at the top represent the traversal of the PCB through the network. So here we can see that if a path is traversed in the opposite direction of the PCB distribution, the up bit is being set. So here we see the first red path that is being traversed from the source A to the destination C. And so we first have an info field followed by 3 hop fields. And in the info field, the up bit is being set as the traversal is against the direction of the PCB dissemination. Then the crossover bit is being set at the last hop field, as we can see in this sequence of hop fields. Then the core segment was initiated by ASA and received by G. So this core segment is also being traversed in the opposite direction of dissemination. So in the info field of the core segment, again, the up bit is being set. And then we have 2 following hop fields for this core segment. Finally, we have the down path segment, the green part of this path. And now we're traversing this in the same direction as the PCB dissemination. And so now the down flag is being set. When the recipient intends to respond to this message, it can simply turn around the hop fields. And we see at the very bottom, the path traversal will be in the opposite direction, or essentially the hop fields will be listed in the opposite order. The info fields are being copied, and you can see how the up-down flags switch directions. Here we see an example of a peering link and the path encoding that includes a peering link. We have the blue up path and the green down path that have a common peering link from E to F that is being used. So in this example, we can see the flags crossover and verify only that are being used to encode this peering link. In the book, you can see the details why all this information is necessary. However, I'll just briefly state that we use additional hop fields for the verification of the MAC fields and to prevent attacks that prevents an adversary from arbitrarily combining these hop fields. An exciting part of the SCION forwarding is the hop field MAC verification. We have message authentication code computation and verification of hop fields that are based on a local AES secret key. In essence, this key does not need to be shared with any entity external to the autonomous system. So it's a key that's only shared by the local border routers and by the beacon server, and again, does not require any external sharing. The computation of the MAC in the hop field looks as follows. The MAC is computed over the timestamp in the info field, the flags, and the expiration time, the ingress and egress interfaces, as well as the previous hop field. So all the hop fields are chained together through these MACs. And this chaining prevents attacks where an adversary attempts to combine arbitrary hop fields together to create arbitrary paths. So in most cases, since the hop field size is only 8 bytes, the MAC computation can be only done over 128 bits. And so a single execution of the AES block cipher in the CMAC mode is sufficient to compute the hop field MAC or also to verify the hop field MAC. It turns out that modern Intel processors have hardware support for AES operations through the AES native interface or AES-NI instructions. And as a result, using these instructions within 50 processor cycles, we can essentially compute an entire message authentication code. This is extremely fast. Note that a single DRAM lookup, if you perform a memory lookup and assuming the information is not present in one of the processor caches, would require 200 cycles. So the entire MAC computation or verification requires a quarter of the time of a single memory lookup. And so this shows how fast this operation can be. Also, an interesting observation is that an AES operation requires less energy than a ternary content addressable memory chip lookup, a TCAM lookup. TCAMs are hardware chips that modern routers rely upon for efficient route table lookups. The downside of TCAMs is that they're very energy intensive. They consume a lot of electricity. And so in essence, an AES operation can, in addition to providing security, also require less energy than modern routers use for regular IP forwarding. And so as a result, we expect that SCION forwarding can be faster and require less energy than even an IP packet forwarding on a modern router. Now that we have discussed the control and data planes in more detail, I invite you to view the next video on the SCION public key infrastructure. The SCION PKI is the key to SCION's secure operation. For more information, please visit our website. Chapter 7 of our SCION book discusses the material we've seen in this video in more detail. You can purchase the book from Springer Verlag, or you can download the PDF from our website. Thank you for watching.